Now we want to talk about molecular polarity.
So we talked at the beginning of chapter 7 about bond polarity. The idea that atoms have different electronegativities, that means that they share electrons potentially unequally. If you have atoms that are the same, chlorine and chlorine, for example, they pull those electrons towards themselves with the same strength, meaning that is a non-polar bond. Atoms that are different, like hydrogen and chlorine, have different electronegativities, unequal sharing of electrons. We call those bonds polar. Okay, there's one side is the positive pole, one side is the negative pole. So, but now we want to talk about entire molecules, which can also be polar. If a molecule contains bonds that are polar, and geometrically they combine to yield positive and negative ends of the molecule is polar. So here's just a diagram of a water molecule. That coloration shows excess in red or depletion of electrons in blue. And so you can see there's more electrons on one side of the molecule, the top in this case, less electrons on the bottom of the molecule. So there's again that slightly negative side on the molecule and a slightly positive side on the molecule. We would call this a polar molecule. So let's look at why water is polar. So it all starts with the Lewis structure, just like everything we've seen previously. Not only the Lewis structure, but the shape. This is a bent molecular shape. So this Lewis structure is drawn in a way to denote shape. So when we're looking at molecular dipoles, we want to always kind of start from that 3D shape. That's why we did that first. So now that we have the shape, we want to look at bond dipoles. Oxygen and hydrogen are different atoms. Each bond is polar, and the dipoles point towards the oxygen. It's right next to fluorine, so it's more electronegative. So in each bond, that would be the case. Now we want to what's called adding the dipoles as vectors. That's going to be, if you know how to do that, great. If you don't, that's fine. We'll see that there's going to be some tricks that come from this, or kind of some guidance that comes from this. But when we're adding them as vectors, basically we're adding in like the different components. You can think like the vertical and the horizontal component. And so the ones that line up add together, so that'd be the pulling up, and the ones that pull in cancel out, right? Because you're pulling in from the left and in from the right, and those are going to cancel out. One of the ways you can think about adding dipoles is like pulling strings. If you were to pull both of those strings at the same time, would you get net movement from that? Because that's really what's going on. The electrons are getting pulled like a string was, and we want to know, is it getting net moved? In this case, they would add to pull up. You will note the two pulling in, those horizontal components, cancel out because you're pulling in from the left and in from the right. It ends up canceling out, and the molecular dipole just pulls up towards the oxygen. So overall, the water molecule is polar. The oxygen side of the molecule would be the negative side, and the hydrogen side of the molecule is the positive side. So it's a top-bottom, not left and right.
The high polarity of water molecules informs all of the properties that we're used to for, like, say, bulk liquid water. So because these molecules have positive and negative sides, those opposites are attracted to each other. So two different water molecules can arrange such that, the positive links up with the negative, and that can just keep going. And so what ends up happening is water molecules are very attracted to other water molecules, and they arrange in such a way to maximize those attractions. This is true of all polar molecules because they always have a positive side and a negative side, and they can link up, in kind of something like a network or like a chain like that. Water just happens to be very, very polar. And so that really informs all of its properties. For one, the fact that water has a really high boiling point. There aren't many liquids that are still around at 100 degrees Celsius. Water is one of the few of those. That's also why it has a really high heat capacity. If you remember, heating temperature was all about molecular motion and how quickly they can move. The fact that these molecules want to kind of arrange in a certain way restricts how much they want to move. And so that makes it more difficult to get water up to a higher temperature because they're kind of locked in, or not locked in, but really attracted to each other in certain arrangements. The polarity of a molecule also determines whether or not it interacts with microwave radiation. So microwave radiation, those certain wavelengths of light, the certain energy of the photons, when they collide with a molecule that's polar, they make the molecule rotate. It has to do with the fact light is electromagnetic radiation. So that electro means that the wave has, basically what ends up happening is the wave has kind of a positive part to it. And that field, the electric field, causes the positive and negative end of the water molecule to align with that field. And the field oscillates as part of the wave nature. And so what ends up happening is this wave just keeps going. So the water molecule just starts, you can see in this instance right here, the water molecule is rotating, and it's just going to keep happening again and again. So this water molecule is going to rotate again and again as this microwave radiation comes in. So these molecules start to rotate, they start to move. That is increased movement. And so this is how microwave ovens work. You put all this microwave radiation in, it causes polar molecules. Water, which is one of the most polar and is abundant in our food, starts to kind of jiggle around a bit, and that leads to heating, right? Then it starts to move around, it hits all of the other molecules. Importantly, most molecules that are in air, it's like nitrogen, so that's a diatomic with the same atoms, so nonpolar. Oxygen, the same atoms, and O2, so that's nonpolar. So these do not get hot in microwave radiation. So that's why when you put your hands in like a microwave, it doesn't feel warm in there, because those molecules in the air haven't been interacting with the microwaves, so they don't get warmed up. But the food that is full of water, those molecules all got jostled around, and that's why that gets warm. And so that's why you can focus on just that. And that's also one of the reasons why, because the microwaves, because it's light, it can penetrate further into the food. So the whole entirety of the food gets heated at a time, as opposed to, like, say, in the oven, where you have to have the heat go in from the hot air into the middle of your food. So polarity shows up in the kitchen.
So let's take a look at just figuring out whether with the polarity of a molecule. Another example, we'll look at CO2. So our Lewis structure there, the carbon is double bonded to two different oxygen atoms. That is linear molecular shape. So now we want to look at the dipoles of each bond. Those are very polar. Oxygen is more electronegative than carbon. It's closer to fluorine. These are definitely polar bonds. They both point towards the oxygen, negative on both sides. And we want to add those dipoles up as vectors. And here we can think this idea, when we're doing that, we're pulling strings, right? You're pulling one to the left and one to the right, equally strong. They're just going to cancel each other out. So you don't end up pulling in a net change to one side. So there's no molecular dipole, and carbon dioxide is a non-polar molecule. It has polar bonds, but the whole molecule is non-polar. In general, polar bonds do not make a molecule polar. A lot of bonds are polar, but in order for a molecule to be polar, you not only need polar bonds, you also need a shape that allows for those positive and negative end of the whole molecule. If we look at carbon dioxide, what ends up happening is the oxygens win in each bond, and so you have a negative and a negative. That's not a polar molecule where you have say like in water, where you have the negative side and the positive side, right? Those are two different ends on the molecule. It is not overall a polar molecule for CO2. So we call it nonpolar. Let's look at some more examples. This is CH2Cl2. That is a tetrahedral molecular shape. Sign those bond dipoles. Chlorine is more electronegative than carbon, but carbon is more electronegative than hydrogen. So all the bonds are, again, polar, and we can see we got these arrows pulling in different directions. If we want to think about adding those dipoles as vectors, we can see the chlorine bonds are pulling out, and the hydrogen bonds are kind of getting pulled in. And so those are not going to cancel each other out. The kind of left and right, or up and down, those do cancel out, but there is a net movement from the hydrogen side of the molecule to the chlorine side of the molecule, right? If some bonds are pulling out and some bonds are pushing in, you're not going to cancel those out, and that's overall going to be a polar molecule. When it comes to CCl4, similar tetrahedral shape. When you go to assign the dipoles now, all of them are chlorine, so they're all pulling out. If we want to add those together, we can see chlorine pulls carbon with the exact same strength for all four of these bonds. So they're the exact same strength, pulling in the exact same outward direction. And so those bond dipoles are going to cancel out, and this is going to be a non-polar molecule. So we can put these four examples, the CO2, the water, CCl4, CH2Cl2, we can kind of group them up. We have the two nonpolar examples, CO2 and CCl4, and the two polar examples, water and CH2Cl2. And so when it comes down to it, it actually is pretty difficult to form a nonpolar molecule because being nonpolar requires everything perfectly canceling, right? You oftentimes have polar bonds, and then how do they cancel out, perfectly cancel out? And so if there's any sort of complication or break from symmetry is where you get polar bonds starting to form. So one of the things was on the water, you have these lone pairs. Those lone pairs take up space. They increase, the electron pair geometry, affecting the shape, moving those bonds out of the way. And so when there's lone pairs there, they're not contributing as a polar bond or anything, but they prevent bonds from pulling in opposite directions. So the reason why CO2 is nonpolar is because that pulled that way and that pulled that way, and they were perfectly opposite from each other. In the case of water, you have pulling out and out, but those lone pairs prevent them from pulling in opposite directions and canceling each other out. In the case of the two carbon-centered molecules, we can see that in the case of CCl4, all of the bonds were pulling the same amount in perfectly opposite directions. No lone pairs to get into the way, nice and non-polar. In the case of the CH2Cl2, we had the chlorines pulling out, which was good, but then the hydrogens were pushing in. And so those were pushing, they were different atoms, which means the bonds had different dipoles, which means you're pulling and pushing in different amounts. That's not going to cancel out. We can put all of these together to give us kind of a nice guidance for whether or not a molecule is polar. So if we have a diatomic molecule, just two atoms, that molecule is going to be nonpolar if and only if the two atoms are the same. If the two atoms are different, it'll be polar. And then an atom-centered molecule, so that's going to be one of these, atoms in the middle with the outer atoms. That molecule will be nonpolar if and only if there are no lone pairs on the central atom and all outer atoms are the same. Both of those must be true for an atom-centered molecule to be nonpolar. So this is kind of a distillation of all the ideas that come from adding up dipoles. So we're not going to need to worry too much about adding dipoles because we can just follow these guidelines. All right, let's look at some examples of determining whether or not these molecules are polar or nonpolar. I have NH3 ammonia, CH4 methane, CSO, that's that molecule on the bottom left, and then HCl. And so all these molecules that I have here, normally if you were given the formula, you would need to get to the Lewis structure. But here we're given the Lewis structures. We're just going to go from that and see what we can do about determining whether or not these molecules are polar. All right, so we'll start with NH3. So we again have that Lewis structure. We know based off the fact that I have 3 outer atoms and 1 lone pair that this thing would be a trigonal pyramidal shape. So we can rewrite our Lewis structure using dashes and wedges to indicate shape, or we can just look at that 3-dimensional orientation. And so when we look at then the bond dipoles, we know the bonds are polar. They're going to pull from the hydrogen to the nitrogen in the middle. And so the thing is, because of this lone pair, right? The lone pair that takes up space in the middle here, we can see that what ends up happening is these bond dipoles, they don't entirely cancel out. They're all pulling in towards the central nitrogen and up. So the in components cancel, but the upward components don't cancel. And you're going to end up with a bond dipole pointing, or molecular dipole pointing to the top of the pyramid, right? That nitrogen is going to be the negative side of the molecule, and the hydrogens on the bottom are going to be the positive side of the molecule. So overall, this is a polar molecule. And H3 is polar, similar to water, quite polar. In this case, again, the non-hydrogen atom, that's where the negative side is, and those hydrogens down on the bottom are all in the positive. And so this was working through the process of looking at the bond dipoles. We could have also noted that because there's that lone pair on the central atom, it has to be a polar molecule, right? The whole reason why these bond dipoles don't add up to cancel each other is because that lone pair takes up space. It pushes them down into that pyramidal shape that they're not all perfectly pulling in opposite directions and able to cancel each other out. CH4, so we can look at that Lewis structure. We know that 4 outer atoms, 0 lone pairs, that's a tetrahedral shape. So we can draw the Lewis structure with either dashes and wedges, or we can look at the 3-dimensional representation of the molecule. If we put those poles, the dipoles for the bonds, all my bonds are polar, all right, and all of those dipoles are pulling in towards the carbon atom, right? They're all pulling in, and they're all pulling in this with the same strength because they're all carbon-hydrogen bonds. So this is a non-polar molecule, right? If you think you're pulling hydrogen in from all these different directions, but they're all pulling in towards the middle, you don't end up getting any net movement, right? If you think about pulling them all in, there's no positive side, no negative side. This is a non-polar molecule. And we could have predicted this because even just looking at the Lewis structure, right? You can just start with the Lewis structure right here and see all the outer atoms are the same, and there are no lone pairs on that central carbon atom. This has to be a non-polar molecule because both of those things are true. That sets us up to be non-polar. You can add up all the bond dipoles, it's fun, but you don't need to. CSO, here's my Lewis structure for CSO. 2 outer atoms, 0 lone pairs. This is a linear molecule, so the Lewis structure was already written as the 3D shape. When I go to add in the bond dipoles, they're both polar. Oxygen is more electronegative than carbon. Sulfur is also more electronegative than carbon. But importantly, sulfur is not as electronegative as oxygen. And so both bonds are polar and they're both pulling outwards. But importantly, they are not pulling with the same magnitude. Oxygen is pulling more electrons out towards it. Okay? And so what ends up happening is there's an imbalance. They don't perfectly cancel. And so this overall molecule, CSO, is polar, right? They're both kind of pulling out, but they're not pulling equally. So, we can see overall there's a net movement to the left, towards the oxygen side of the molecule, because the sulfur isn't pulling quite strong enough to overcome how strongly that oxygen is pulling electrons towards it. And whenever we could have just looked at the Lewis structure and just seen, I got oxygen as 1 outer atom, sulfur is a different atom that's also on the outside of this molecule, that has to be polar. In order to be non-polar, it has to perfectly cancel. You have to have the same outer atom. These are different. They're not going to cancel out. It's going to be a polar molecule. All right, HCl, Lewis structure, it's just a hydrogen and a chlorine atom. So that's just 2 total atoms. Its shape is linear because it's just 2 atoms. And so they're just touching each other. They still form a nice straight line. When we go to assign bond dipoles, it's just the dipole of the bond. And so the molecular polarity of this is just going to be the same as the bond polarity. And bond polarity is determined by, are they different atoms? So these are 2 atoms, they're different. This is going to be a polar molecule. HCl is a polar molecule. Whenever you're dealing with a molecule that is only 2 atoms, the question just becomes, is the bond polar? And we determine whether or not bonds are polar based on whether or not they have the same 2 atoms or different atoms, right? Different atoms, yes, it's polar. Same atoms, that's a non-polar bond. So Cl2 and Cl2, that's non-polar. That'd be a non-polar molecule.